videos, and today also we are going to discuss some of the techniques or some of methods that you can apply in non-parametric statistics. So if you can remember, last time we discussed when you have a sample, when you want to check the randomness of a sample, we use the runs test. So if you have two samples, right? If you have two samples, in that case, if you want to test whether there is a relationship between these two samples, right, or whether these two samples are coming from the same distribution or not, in that case, we can use this Wolfowitz two sample runs test, right? So the two sample runs test, right? We use this in order to check when you have two samples, whether the two samples are from the same distribution or not. So when you write the hypothesis, your null hypothesis is two samples are having the same distribution, or they are coming from the same distribution, where your alternative hypothesis is two samples are not from the same distribution. Now, when it comes to this test, when it comes to the test statistic, denoted by capital R, this is equal to simple R, that is the number of runs. Right? So I will explain you how to calculate the number of runs, okay? And then what we do is we take these two samples and we combine the two samples, and then we calculate the number of runs we have, and then that we take as simple R, that is our test statistic. And then we calculate the p-value. So to calculate the p-value, you have to check whether your number of runs are even or your number of runs are odd, right? So if your number of runs are even, you can use this equation to calculate, right? Or if your number of runs are odd, you can use this equation to calculate the p-value, right? So when it comes to the decision rule, how you take the decision, right? When the p-value is less than 0.05, that is our significance level, you can reject H0. Right, that would be our decision rule. So it's very easy. So I'll just explain you using this example. So it says, assume that there are two samples with 8 observations from the two production lines, and we measure output voltage at a key test point of the individual products. So let's say there are two production lines. Let's say they are producing some electronic item, right? So from these two production lines, they have taken 8 products from each production line. So we need to check whether there is a difference between these two production lines, right? So in that case, since you have two samples, and since we want to check whether there is a difference between these two samples, we can go to two sample runs test. So our hypothesis would be H0. You can write the two samples are coming from the same distribution, where you can write the alternative hypothesis as the two samples are coming from different distributions, right? Okay, so what is the first step? Now, as the first step, when you have two samples like this, what you have to do is you have to arrange your you have to combine both samples and arrange them in ascending order. That would be the first step, right? Arrange them in ascending order. So you can see I have taken the values, that is from each sample I have 8 values, so altogether I have 16 observations. So I have put all the 16 observations together and I have arranged them in ascending order. You can see the minimum is 10.3, but the maximum is 27.45. And then after arranging these values in ascending order, what you have to do is you have to check or you have to label these observations with the sample name. Now since I have two production lines as A and B, so you can see 10.3 is coming from this production line B. Here we can see 10.3. So I have named it as 10.3 is coming from B. And if you take 10.9, again it's coming from B. So I have named it as B. Then if you take 12.75, it's coming from sample A, or the first sample. So I have named it as A. So likewise, you have to label each observation with the sample name. And then what you have to do is, now you can check the number of runs. We know if when we discuss the runs test, right, after putting the positives and negatives, when you take a set of values, set of positive signs or set of negative signs, you consider it as a one run. So likewise, when you, after labeling all the observations with the sample, right, when you take a set of characters or set of observations which are having the same sign or which are coming from the same sample, we call it as a run. So you can see in this case you have BB, so that is a one run. So you can take this one as a one run, right? And then you have 3 A's, so you can take this one as another run. And then you have another B, only B, so that is a separate one, another run. And then again you have another A, so that is another run. Then you have another B, so again that is another run, right? And then you have 2 A's, so you can take these 2 A's as another run, right? And then you have a B here, you can take it as another run. And then you have a A here, you can take it as another run. And you have B here, you can take it as another run. You have A here, you can take it as another run. And you have 2 B's, finally we can take it as another run. So likewise, we can identify the number of runs after pooling all the observations of the two samples. Now we can count the runs. Here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my test statistic, simple R, is the test statistic which is denoted by capital R. So that is the number of runs, so that is equal to 11. Now you can see my number of runs are odd, right? It's an odd number. So what you have to write now? You have to write this number of runs as in 2k plus 1 format, right? So when you write 11 into k plus 1 format, that is, we know 2 into 5 plus 1. This is equal to 11, right? So as according to this set of observations, my k value, you can see k value is equal to 5. K value is equal to 5. Now you have the option here, right? See, you can use this formula, that is to calculate the p-value, right? So n1 is n1, n2, you can take any sample. Now in this case, in the first sample also you have 8 observations, in the second sample also you have 8 observations. So your n1 value is 8, n2 value is 8. Now we recognize the k value, it's 5. Okay, so n1 plus n2 would be 16, right? So by substituting all of these here, you can solve this and find out the p-value. So after finding out the p-value, you can take the decision. That is, the decision would be, if the p-value is less than 0.05, we can reject H naught. So I'm not going to calculate the p-value. So you can just calculate it and see whether you can reject H naught or not. If you reject H naught, that is the samples are not coming from the same population. If you do not have enough evidence to reject H naught, so you can conclude that the two samples are coming from the same population. So it's very easy to conduct. It's just a matter of how to recognize by the number of runs after pooling all the observations and arranging them in ascending order. Right? Okay, so the things that we discuss about test, how to use the test when you have one sample, and how to use test when you want to test the randomness, right? And the next procedure is when you want to do testings about two related samples or two dependent samples, right? So again, we have some non-parametric method. So that is like a very easy one. We have the sign test, right? And the Wilcoxon test, which we already discussed when we have one sample. So the same process we can apply when you have two dependent samples and you want to test, or you want to conduct a hypothesis regarding its mean. All right. So in this case, there are some assumptions that you have to satisfy, right? So variable should be in continuous scale, right? And it should be interval, ratio, or ordinal level. So the paired observations for each observation should be independent, and the difference scores, for an example, the differences between the paired observations, so it should be coming from a continuous distribution. So based on these assumptions, if you have two samples and if you want to test, and if these two samples are dependent, and if you are interested in testing about a mean of these two samples, you can use a sign test or you can use the Wilcoxon test. So how to write the hypothesis, p-value, the decision rule, it's all exactly like this, the sign test. So I will just go through with this example and will explain you, right? So it says, consider a clinical investigation to assess the effectiveness of a new drug designed to reduce repetitive behavior in children affected with autism. If the drug is effective, children will exhibit fewer repetitive behaviors on treatment as compared to when they are untreated. A total of 8 children with autism enroll in the study. Each child is observed by the study psychologist for a period of 3 hours, both before treatment and then again after taking the new drug for 1 week. The time that each child is engaged in repetitive behavior during each 3-hour observation period is measured. Repetitive behavior is scored on a scale of 0 to 100. Scores represent the percent of the observation time in which the child is engaged in repetitive behavior. For example, a score of 0 indicates that during the entire observation period, the child did not engage in repetitive behavior, while a score of 100 indicates that the child was constantly engaged in repetitive behavior. The data are shown. So what has happened? There are 8 children who are suffering from autism. So what they have done is, there is a new drug. So they want to test whether this new drug is effective or not. So what has happened? If they use this new drug, if it is effective, it should reduce the number of repetitive behaviors that these children are doing, right? So before the treatment, they have based on a score from 0 to 100 scale. They have measured the repetitive behaviors, and after 1 week, after the treatment also, they have recorded the repetitive behavior. So if the drug is effective, that drug should minimize the repetitive behavior, right? So in this case, so you have to test whether there is a significant improvement after treatment, right? So I'll take it like this. So I'll take, let's say, MB. So this one I'll take as the median. This is the median repetitive behavior. Before the treatment. This is the median repetitive behavior before the treatment. Just like that, I'll take MA. This is the median repetitive behavior after the treatment. Right, this is after the treatment. So if the drug is effective, right, these values should represent a lower number because the drug is reducing the repetitive behavior. So you have to test whether the drug is effective or not. So the claim we have to always take as our alternative, right? So if it is effective, the median value of this is lower than the median value of the first set, right? So that is, if you take the difference, that is MB minus MA, this should be greater than 0, right? And in this case, the opposite you can take as the alternative hypothesis, that is MB minus MA. This one is less than or equal 0. Right? So this is our hypothesis. So you just read the question. You have the same child, right? You have the measurement of the same child. So this is dependent, two dependent samples. So you have to read the question, identify what you have to test, and then you can use in the median values. Right, so in the non-parametric, if I say mean, so non-parametric, it represents the median, right? So you have to take the median value as the parameter, and then you have to write the appropriate hypothesis. Now the hypothesis is okay. Now you have to find the test statistic. So to find the test statistic, what we do is, just as we are conducting the one sample sign test, we check the number of positive differences and number of negative differences, right? And we know first, when we look at our alternative hypothesis is having the greater than inequality. So when our alternative hypothesis is having the greater than inequality, that is our test statistic is equal to n minus, right? Our test statistic is equal to n minus, that is the number of negative differences. If you have the less than inequality for your alternative, so our test statistic is number of positive differences. If you are doing a two-tailed test, right, you are testing for equal, not equal, you have to check the number of positive differences, number of negative differences, and you have to take the minimum one as your test statistic. So same as we did for the one sample sign test, right? So we have to now check the positive differences and the negative differences. So I'll just write it here. Now if you look at the first observation, here 85, here 75. 85 minus 75, so that is negative. And then you have 70 minus 50. So again you have a negative difference. And then let's say you have 40 minus 50, again a negative difference, right? And then you have 65 minus 40, that is a positive difference. And 80 minus 20, that is a positive difference. 75 minus 65, that is again a positive difference. 55 minus 40, positive difference. Then 20 minus 25, negative difference. So this is the values that you get by considering the sample. So here you have 1, 2, 3, 4. 4 positive ones and 1, 2, 3, 4 negative. So our test statistic is number of negative differences you have in this sample. So in this case, you can write down your test statistic value is equal to 4. You have 4 negative differences. Now you can calculate the p-value just as you calculated in the one sample sign test, right? P-value is equal to the probability, right? Where when you take this test statistic S, this is less than or equal to the observed value of the test statistic, that is 4, right? Given that S is having a binomial distribution. So S is having a binomial distribution. So here the sample size is 8 because when we paired we have only 8 observations, and here you have to take 0.5 as the success, probability of a success. Now we have to read this from the binomial table, right? So we take the binomial table here. Now our sample size is 8. So I'm going to read 8, right? So you can see here you have the 0.5 is here, the probability of a success. So when it comes to sample 5, our S-naught value is 4. So this is the cumulative binomial table. So with the corresponding value is 0.6367, right? So the p-value you can write as 0.6367. Okay, that is the p-value. So we can see in this case our p-value is greater than 0.05. So that is, hence we do not have enough evidence to reject H-naught, right? So that is, we cannot conclude that this new drug is effective. So just like that, it's very easy, right? But after pooling, you have to apply the one sample sign test procedure. No, nothing is different, the same thing, in order to find out about the difference between two medians, right? So there is another question which you can try at home. Now, if you want to apply the Wilcoxon sign test to two paired samples, that is also possible, right? You can apply the Wilcoxon sign rank test as well, right? So let's see how to apply the Wilcoxon sign rank test. I'll explain you how to write down the hypothesis, the decision rule, everything by using this example. So it says a study is run to evaluate the effectiveness of an exercise program in reducing systolic blood pressure in patients with prehypertension defined as a systolic blood pressure level, right, that is 120 to 139, right, or diastolic blood pressure between 80 to 89. So a total of 15 patients with prehypertension enroll in this study, and their systolic blood pressure are measured. Each patient then participates in an exercise training program where they learn proper techniques and execution of a series of exercises. So patients are instructed to do the exercise program 3 times per week for 6 weeks. So after 6 weeks, again the systolic blood pressure is measured. So you have the data. So they are asking whether there is a difference in systolic blood pressure after participating in the exercise program as compared to before, right? So same set of patients, you have recorded the systolic blood pressure before they go through with the exercise program, and then after 6 months after they went through with the exercise program, right? So let's take M1 as the median systolic blood pressure before the exercise program, right? And then we can take M2 as the systolic blood pressure after the exercise program, right? So let's see what you can do. Now we have already written the hypothesis, right? So hypothesis is done. Now how to calculate the test statistic, right? So just as we did in the Wilcoxon sign rank test, first you have to calculate the differences of these 2 samples, and then what you have to do is you take the differences, you take the absolute value of the differences, and then you have to rank the absolute value of the differences, right? We'll do it. I'll just take a table here, that would be easy for us. So I'll insert a table since that would be easy for us. Okay. So here, first one, we have the first observation is 125 minus 180. So that the difference is equal to 7. So in the next one, you have 132 minus 134, that is you have minus 2, and then we have 138 minus 130, that is plus 8, and then we have 120 minus 124, that is minus 4, and then we have 125 minus 105, that is plus 20, and then we have 127 minus 130, that is minus 3, right? So that is minus 3. Minus 3. And then we have 136 minus 130, that is plus 6. 139 minus 132, that is plus 7, right? Plus 6 and plus 7. So you have 6 and 7. And then you have 131 minus 125, 3, right? So that is minus 8. So this should be minus 8, right? And then 132 minus 128, that is minus 4. The next value is minus 4. And then you have 135. Sorry, I have done a small mistake. In this case, 131 minus 123, that should be plus. 132 minus 128, that is plus 4. Then 135 minus 126, right? Again plus 9. So this should be plus 9. This should be plus 4 plus 8. Right, and then you have here 100. Then you have 136 minus 140, so that is minus 4. This is minus 4. And then you have here 128 minus 135, so that is again minus, right? Minus 7. And 127 minus 126, that is plus 1. Minus 7 and plus 1. Minus 7 and plus 1. And the last value we have 130 minus 132, that is minus 2. So likewise you take the difference and then you can, by taking the two values, you can just calculate the difference of the two observations. So after calculating the differences, we know what you have to do. Okay, we have to just arrange all the things in ascending order, or we have to give the ranks, right? By considering all the values, considering values without the sign. That is, we have to consider the absolute value and rank all these observations, right? So let's rank. Now you can see the first, the minimum value is 1. Okay, here the minimum value is 1. And then you have only 1 here. And then when it comes to 2, you have 2 2's, that is, you have 2 here and you have 2 here. So if you give 2 and 3 ranks for this, so you have to take the median value. So 2 plus 3 divided by 2, that is again 2.5. So we have to give 2.5 to each cases, right? And then 3. So here you have only 1 3, so we have used ranks up to 3. So 3 here you have to give the rank as 4. Okay, and then for 5, yes, the next value is 4. So here you have 1 4, here another 4, and here another 4. 3 4's. So you can give 5, 6, 7 as the ranks. 5 plus 6 plus 7, and then again you have to divide it by 3 to give the rank for 4, that is 6. So for this 4 you can give 6, for this 4 6, and for this 4 6. Now we have used up to 7. So let's see whether we have 5, we have no 5, and whether we have 6, we have only 1 6. So we have used up to 7, so this will be 8. And we have 7's here, we have a 7, here we have a 7, 3 7's. So for 7 we can give 9, 10 and 11. So that you can divide by 3. So that would be 10. 30 divided by 3, that would be 10. So for this you can give 10 for 7. Right? And then if you take now for 7, we gave up to rank 11. And the next one 8. So you have 1 8 and here again another 8. So you can give 12 and 13. Right? And when you divide it by 2, 12.5. So here 12.5, for this 8, 12.5. And let's see the next number 9. So we have used up to 13. So 9 would be 14. And then the last one is 15. So we have ranked everything. Now in this case, so when you write the hypothesis here, now you have to check whether there is a difference between the systolic blood pressure levels after participating in this exercise program. So since you just want to check whether there is a difference or not between these medians or between the systolic blood pressure levels, right, you can conduct a two-tailed test, that is M1 equal M2 versus you can take the alternative as M1 not equal M2. This is your hypothesis. So now when you have a two-sided test in the Wilcoxon sign rank test, I hope you can remember after giving ranks to these observations, what you have to do is you have to then calculate the test statistic. Right? How do you calculate the test statistic? Now you have to check the ranks of the positive values. Take the total of the ranks of the positive differences. Take the total of the ranks of the negative differences. Take the minimum as your test statistic. So let's see how we calculate. First we'll calculate the total of the positive differences. So 7 is a positive one. So the rank value is 10. And then you have 8 is a positive one. Rank value is 12.5. Then 20 rank is 15. Then you have 6 rank is 8. Then 7 rank is 10. And then 8 rank is 12.5. And 4 rank is 6. 9 rank is 14. And 1 rank is 1. So that is when you take the total of the ranks of the positive differences, that is 214. So let's take the ranks of the negative differences starting from -2. Right? So you have 2.5. And then you have 6. And then you have 4. And then you have again 6. And then you have 10. And finally you have 2.5. So that will sum up to 31. So the minimum between these two is 31. So that is your test statistic. Now we have to, in order to take the decision, we have to read the table value just as we did in the one sample Wilcoxon sign rank test. So we are going to read the Wilcoxon sign rank table. Okay. So we are doing a two-tailed test. Our significance value is 0.05 and our sample consists 15 observations, right? So our table value is this 25. So we can easily read the table value. So our table value is 25 here. So you can put 25 here. That is our table value. And then what we can do is now we have to take the decision. Right? How we take the decision? If our test statistic is less than our table value, right? If our test statistic is less than our table value, we can reject H0. But in this case, our test statistic is 31 and our table value is 25, where our test statistic is greater than our table value. So we can write, since 31 is greater than 25, we do not have enough evidence to reject H0. Right? That is, if you can't reject, if you do not have enough evidence to reject H0, that is, we can conclude that there is no difference between the systolic blood pressure levels of these patients, right? It's very easy, just as we did the one sample sign test and the Wilcoxon test for one sample. You have to just take the difference and take that set of value as a one sample and conduct the sign test and the Wilcoxon test when you have two paired samples, right? So I hope you understood. So I hope explaining through these doing exercises would help you, right? So that's why I took this one and explained you. So I hope you understood how to conduct that test. And I hope we'll stop at that point, and in the next session we will discuss how to conduct test when you have more than two samples. What are the non-parametric procedures that you have to apply? So there's another exercise in this one. So you can apply the sign test and the Wilcoxon test and see what will happen with the decision, right, when you apply the two methods, right, to the paired data set. So then, thank you so much. We'll meet with the next session.